Swayam Prabha. Digital India. Educated India.
Now, with that background, let us study 3 or 4 properties of the transformation operators. The first, and once again we are going to use this in a later discussion. The first property is that the transformation operators leave the scalar product of 2 functions unchanged. Remember what is scalar product, dot product? How was it defined? What is Fij? In case you do not remember, I have written it here. This is how you write it, Fi comma Fj in brackets, and is defined as integral over all space Fi star Fj, right. Fi star is a function of say x1, x2, x3, Fj is a function of x1, x2, x3. What are we dealing with here? We are dealing with functions, right, which can be represented as linear sum of the Cartesian coordinates x1, x2, x3. I could have written xyz, but x1, x2, x3 is more symmetric than xyz. Good thing is that I can just change the subscript and go from one to other. That is why I have written x1, x2, x3. Okay. Do we remember that this is the scalar product of Fi and Fj? So, what I am now saying is that the scalar product of ORFi and ORFj is the same as the scalar product of Fi and Fj. Understand? Let us prove that. You agree with this? Fi star in terms of x1, x2, x3 is ORFi star in terms of x1 dashed, x2 dashed, x3 dashed. Transformed function in transformed coordinates is the same as original function in original coordinates, right. So, I could see the understanding being switched on a little bit in your faces now. So, what we are saying earlier, now that is this is the relevance. Okay, so, I have worked out the easy one. Can you work out the difficult one? What is Fj, x1, x2, x3? Yes, over Fj in terms of x1 dashed, x2 dashed, x3 dashed. And now see, if you now look at this, does not it almost look like the scalar product of ORFi and ORFj? What is left to make this a scalar product? dx1, dx2, dx3 is there. Instead of that, if I can transform to dx1 dashed, dx2 dashed, dx3 dashed, right. And that is what we are saying a little earlier, is not it? That when we work with a volume element, it does not matter if I write dx1, dx2, dx3, or if I write dx1 dashed, dx2 dashed, dx3 dashed. Volume element, very small volume element, they are the same. So, without any prick of conscience, I can write dx1 dashed, dx2 dashed, dx3 dashed instead of dx1, dx2, dx3, right. We have substituted Fi star by ORFi star in the transformed coordinates. I have substituted Fj in the original coordinates by ORFj in transformed coordinates, and I have written the volume element in transformed coordinates as well. So, if you agree with that, then do you see that on the left hand side I have the scalar product of Fi and Fj. What do I have on the right hand side? The scalar product of ORFi and ORFj, right. So, what we have done essentially is that we have proved this. Scalar product of the transformed functions is equal to the scalar product of the original functions or in other words, transformation operators leave the scalar product of two functions unchanged. Okay. So, at the moment we might be, it might seem that we are talking about something that is completely arbitrary, very far away from chemistry, very far away from symmetry. It is not. We are going to just be a little patient, 2 more classes, and we will be back where we started from with a little better understanding. Next, transformation operators are linear. What is the meaning of transformation operators are linear? We can consider 2 cases here. First is, let us say f and g are 2 functions, a is a number, a scalar, and g equal to af. In this case, if the transformation operator is linear, what should I write? That OR g should be equal to a into OR f, isn't it? Then it will be linear. And the other case is, if f, g and h are 3 functions, so that h equal to f plus g, then OR h should be OR f plus OR g, right. An example of a linear function, sine theta plus phi equal to sine theta plus sine phi? No, definitely not. So, not everything in the world is linear. Okay. So, what is an example of a linear function? A linear operator, sorry, yeah, linear operator. So, let us prove, let us see whether transformation operators are linear. Are all operators linear? No, we just saw, right? Then not everything is linear. Are these linear? Let us see. Let us start with this. By now I think you will agree with me if I write ORG in terms of the transformed coordinates is equal to G in terms of the original coordinates. Will allow me to write that. Now, what is G? G is just A multiplied by F. We wrote G equal to A multiplied by F. What will be the next step? What is F? F x1, x2, x3. What is that? ORF x1 dashed, x2 dashed, x3 dashed, hence proved. What do I have on the left hand side? ORG, right, in x1 dashed, x2 dashed, x3 dashed. On the right hand side we have A multiplied by ORF in the same base, right. So, essentially what we have proved is ORG is equal to A multiplied by ORF. They are both in the same base. So, if this was in x1 dash, x2 dash, x3 dash and that was in x1, x2, x3, then there would have been a problem. You have to convert to the same base, that is all. Once we convert to the same base, you do not even have to write it, right. So, you convinced it is linear, hey, wake up, do not fall asleep. Linear is boring. If it was non-linear, it would have been easier to stay awake. I agree, but what can I do if they are linear? Okay, let us take the more interesting example, F, G and H. Okay, oh, I forgot that there was a highlight here. Anyway, sorry. I think you will allow me to write this pair of equations. ORF in the transformed coordinate system is equal to F in the original coordinate system, and then ORG in the transformed coordinate system is equal to G in the original coordinate system, right. So far so good. So, now what do I want to see? I want to see whether ORF plus G is equal to ORF plus ORG, right. So, let me write like this. Is this okay? Huh? Is that okay? ORH in transformed coordinate, that should be equal to H in the original coordinates. What is H? F plus G in original coordinates. I will write like this, f in x1, x2, x3 plus g in x1, x2, x3. Now what will I do? What is f x1, x2, x3? It is OR f in x1 dash, x2 dash, x3 dash, right? And what is g in x1, x2, x3? OR g in x1 dash, x2 dash, x3 dash. Hence proved. The background music was very timely. It came almost at the time of the climax. Not very, almost timely. You see that or not? ORF plus G equal to ORF plus ORG. Everything in the same base. That is what we have proved. Alright? Achal, question? No question? Good. Next, I think I have only one more after this. We are almost done. This will take some time. Transformation operators are homomorphic with symmetry operations. What is the meaning of homomorphic? Similar structure. Similar structure. So that means if you work out the group multiplication table, they should be of similar structure. Okay. Let us start with this. Let us do the derivation and let us see where we get. Let us say S, R, T are once again 3 operations and T equal to SR. That means if you start from here, start with this coordinate system x1, x2, x3. Okay. Perform the R operation, you get, let us say, x1 dash, x2 dash, x3 dash. Perform S on x1 dash, x2 dash, x3 dash, you get x1 double dash, x2 double dash, x3 dash, x3 double dash, right. And then since T equal to SR, I can draw this arrow here and go directly from x1, x2, x3 to x1 double dash, x2 double dash, x3 double dash by operation of T. Yes. So, will you agree with me on this? OTF in x1 double dash, x2 double dash, x3 double dash is F in x1, x2, x3. I know it is getting a little boring, we are saying the same thing over and over again, but then the thing is I have no option but to go through this if I am to derive great orthogonality theorem. Okay, right. So these are like necessary evils. Okay with this? Same boring old thing, right? Transformed function in transformed coordinate is the same as the original function in original coordinates. That's all. Similarly, OSG in terms of the double dash coordinates is G in terms of the dashed coordinates. So now let us say G equal to ORF. We are transforming the coordinates so far, now we are transforming the functions. Let us say G equal to ORF. Will you agree with me on this now? I have just written ORF in place of G in the same coordinate system. G equal to ORF, I have just added the bases x1 dash, x2 dash, x3 dash on both the sides, right? Now, but then ORF in x1 dash, x2 dash, x3 dash is nothing but F in the undashed coordinates, right? Is jugglery. It is very simple jugglery, only one concept. So then what is OSG in x1 double dash, x2 double dash, x3 double dash? First of all, instead of G I can write ORF, right, and right hand side I get F x1, x2, x3 which is equal to OTF in the double dashed coordinates. So, you basically get the same thing that we were saying earlier, you get the same character table. So, you get the same group multiplication table no matter whether you use the symmetry operations or the transformation matrices or the transformation operators, right. Last for today and the most important, transformation operators produce, and we are back to our favorite term, unitary representation if orthonormal basis functions are used. So, now see we are slowly homing into the actual take home message. What we are going to show tomorrow is that you take any representation. It is possible to perform a similarity transformation and make it unitary. Eventually, we are going to deal only with unitary representation, okay, and there is a reason why. So, we will see tomorrow that you can convert any representation to a unitary representation by a suitable similarity transformation. So, before that, this is something that we need to understand, that transformation operators produce a unitary representation when you use orthonormal basis function. Have we looked at an example of this already? Does it ring a bell, or are we too confused with these ORs and DRs and dashed and double dashed and all that? Remember those transformation matrices that we had talked about using XYZ once again? Had we not shown that they are orthogonal? Huh? Orthogonal is a special case of unitary, right? So, essentially we are proving the same thing. We have demonstrated what we are saying now already using the transformation matrices that we obtained using XYZ. A quick check, okay, that time we talked about matrices. So, we got not only unitary matrices, but also orthogonal matrices, not orthonormal, orthogonal matrices, because they are all real. If they are not real, then they would have been unitary, that is all. Okay. So, something that we have demonstrated already using C3V transformation matrices and XYZ base, we are going to show that now for a general case, but the message is that transformation operators produce a unitary representation if you use orthonormal basis function. And to do this we start from something that we learned a little while ago, that the scalar product remains the same. Okay. The scalar product of the transformed functions is the same as the scalar product of the original functions. Okay. Now, you are using orthonormal basis functions, right. So, I am allowed to write this, that the scalar product of the functions is what? Kronecker delta, right, okay, which implies that the scalar product of the transformed functions is also Kronecker delta, right. I hope you have not forgotten this. What is ORFI? So, in this slide essentially we are summarizing everything that we have discussed today. Sum over k d k I r f k, that is ORFI, and ORFJ is sum over L equal to 1 to n d L j r f j f L, sorry, f L, alright. Remember this? So, now what is the definition of scalar product? Integral f1 star f2 d tau. So, if I write that integral, I get this a little bit scary looking integral, but it is not actually scary. It is just integral f1 star f2 d tau. It is just that f1 is a little big. Okay. Is it still scary or is it okay? It is fine, not scary. So, now let us make it a little less scary again. So, I have integral, I have summation, it is scary to me. I get scared when I see an integral sign, and to make things worse I have two summations as well. So, I would like to get rid of as many of these as possible. Okay. How can I get rid of this? One thing I can do is that I can try to collect the integral I can take the summations out anyway, right. We are integrating over what? We are integrating over all space, right. Space not necessarily your Cartesian space, space function space. Okay. Now, so if I am integrating over function space, will you allow me to take these d, the matrix elements outside the integral sign and leave only the functions inside integral sign? Huh? That will scare me a little less. May I do that? Huh? What will I write then in the next line? Sum over k dki r fk, no fk, right. Sum over k dki r, then sum over L dlj r integral fk fl d tau, right. And when I write integral fk fl d tau, life becomes a little simpler. Why? Because I am using orthonormal basis functions, right. So, this is what it becomes. That is the dot product of orthonormal basis functions, that is also Kronecker delta, right. Kronecker everywhere. So, now how does that help me simplify in something? What are the terms that will survive? What is the meaning of Kronecker delta? It is equal to 1 when k equal to L and is equal to 0 for k not equal to L. What is the variable, k or L? I am summing over k, summing over L both, but I want to get rid of 1 at least, right. So, let me get rid of 1. Can I get rid of 1? I have just written delta KL here, I have not done anything more. How do I get rid of 1? Like this. I can get rid of L, put L equal to K, only those terms will survive. So, I still have one summation, but okay, I can live with one summation, I can work it out. Two summations is a bit too much. So, sum over K dkl star dkj is equal to delta ij. What are these? These are matrix elements. Okay. Now, what we can do is we can put in explicit values, k equal to 1 to n, right. So, to start with, put k equal to 1. Put k equal to 1. What do you have? d1ir star d1j r, right. So, what is that going to be? That is going to be 1 when I equal to j, and it is going to be 0 when I is not equal to j. So, if you go on expanding this, what are you going to get? If you go on expanding this, will you not get the unit matrix? This is what you get, right. So, if this is what is satisfied, is that not the condition for the matrices to be unitary? You look at this, see this is Ki and this is Kj, right. So, this is basically you are working with the matrix elements of this Hermitian, Hermitian conjugates or adjoints. So, the adjoints multiply to give you the unit matrix, that is the matrices are unitary. Okay. So, this is the most important message that we have taken today. Everything else was really preparing for this, that transformation operators produce a unitary representation if orthonormal basis functions are used. Okay. We stop here today.